Alright everybody, here we are with another educational video on the rocks in the Ainsa Basin in Spain. So looking at Eocene deep marine deposits. And you know, we've looked at some sandstones, we can look at some limestones, and for those of you that know me, I like all rocks. So you're not a complete geologist unless you also appreciate the mud side of the story. So as that forms a significant portion of your basin fill typically, we are standing here on pretty much a pile of mud. And we're located in a position that is atop of the last of the big deep water depositional coarse grain deposits, but before we get into a prograding delta deposit. So the mud here, it's, as you can see, very light gray colored. It's very calcareous, it's very bioturbated. It still has a little bit of clay in it, but it is essentially composed of significant amounts of biogenic carbonate material raining down from the water column. So now what's interesting at this outcrop, and you may already have noticed, there are some features here. These sort of big round shaped orangey brown things, and you see a whole bunch of them in the outcrop here. Those are concretions, and they're composed of carbonates, iron rich carbonate, and they form near the seafloor due to the action of microbes eating up organic matter in the sediment and precipitating out carbonate. So they're evidence that the sedimentation rate here is low enough for this material to be chewed up near the seafloor and build these fairly large concretions. So very cool. Now why do I care? Well, we're actually standing on the maximum flooding surface of the entire depositional system. What is a maximum flooding surface? If you read the definition, it is very simply the surface that marks the transition from retrogradational stacking to progradational stacking patterns. That's all it is, okay? What that means is that that is the surface across which I have the most reduced sedimentation rate in the basin. And I made a little sketch of that to kind of point to you why we care. So what I've kind of drawn here is a clinoforming marine system, very strongly vertically exaggerated, where we can see some basal packages that are backstepping or retrograding, and then packages coming out and prograding over the top of that. So this surface here in green marks the maximum flooding surface. It is simply the surface across which I change from a retrograding to a prograding stacking pattern. Now why is that surface really useful? It is the surface across which, particularly in the basin, I have significantly reduced sedimentation rate. Now that can mean, in this case, that I get these carbonate concretions that are chewing up organic matter available, but it might also mean that where that organic matter has not been chewed up, that might be the best places where you can go and find marine source rocks or unconventional reservoirs. Now in this case, given that the organic matter has been chewed up and the TOC is very low, if we think that there is an organic rich rock out here, you'd probably go further up this surface here to find organic rich rock. Now you can see there's a lot of downlaps on here, so this is often called the downlap surface. Those are the downlaps, or the four sets of the clinoforms that prograde over on the top onto the bottom sets of the preceding succession. So chasing a downlap surface is a really useful thing to do in your basin scale stratigraphy to figure out where you might find your best marine source rocks. Often I'll hear people say, but I don't have downlap surface, I don't have clinoforms. Well, make sure if you do this interpretation, 10 to 100 times vertical exaggeration of your seismic, otherwise you're not going to see it. And obviously, if I'm way out in the basin, I don't have clinoforms, it's all bottom sets. If I'm way up dip, I'm an all top set. So there is a narrow band where you're going to see that downlap surface, but once you found it, you can trace it a long way.